Hi everyone. So we're going to look at one last thing before we move on to bigger and better things, and that is bit masks. So I wanted to show you quickly at how bit masks might work and why we actually had to look at binary. Now, originally my plan was to actually look at this subject well before, earlier in the term, and then we sort of ran out of time before we moved on to. I had to go on to other subjects just so I can get ready for the midterms. And as a result, it might seem out of place. Originally, I wanted to do it immediately after talking about binary and two's complement because it's so tightly connected with those topics. So you may have been wondering this entire time why we have this thing right here, the double and. Why not a single and? I remember as an undergrad, I always thought Java and C++ were insane that they had this, we have to have a double and if you put a single and, it won't give you an error. Some weirdness happens. And it was only when I went off into industry when I started realizing what the actual weirdness was or why it existed at all. That's because it's a what's called a bitwise AND. It's a bitwise operator. There's a number of those bitwise operators, but double AND and double OR are the big ones. So what does this actually mean? This a bitwise operator, let me frame it a different way. Double AND means logical AND. It is a buff is not equal to null, and a buff at position 0 is not equal to the tab character. Fine, that makes sense. A single AND is a bitwise operator, as in I will take one number, I will take another number, and bit by bit through those numbers, I will actually compare them. And if they're in the case of an AND, if they're both ones, the resultant bit in the same number, its same position, will be a 1. And if it's not, they're not both ones, then it will be a 0. Now, it makes a lot more sense if we just show you an example, but I just wanted to, say it out loud what the heck this thing is doing. And this is one of those crazy parts of C and why, why we have to look at how binary actually works. So here is a bitwise AND. So -1 and 5 is equal to 5. What? Okay, 0 and 5 is equal to 0. Okay, 0 or 5, the bitwise OR, is equal to 5, and -1 or 5 is equal to -1. Okay, what's going on here? Let's take another couple examples. Those are actually, notice that the -1 and the 5 give you back the original number, and 0 or the 5 gives you back the original number, but a -1 or 5 gives you -1, and a 0 and 5 gives you a 0. So you either have the first number or the second number because of this -1 and 0. Notice that -1, however, is, so in case you forgot, you got a 1, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right. And 0, as you may have guessed, considering, yeah, you should have guessed at least by now. It's all zeros. Okay, I got an extra 0. No, perfect. There we go. Whole bunch of zeros. That's what a bitwise operator is doing. It's going bit by bit comparing. And therefore, what I would get with a 5 and all of this. So let's do 5. 1, 0, 1, and a 0. And then I got a bunch of zeros here all the way across. If I have a bitwise and, what do? I see this one and this one. What do I get? Well, it's a 0 and a 0, therefore it's a 0. 0 and a 0, 0. 2, 5. 1, 2, 3, 4. 1, 2, 3, 4. Bit by bit, I go 0 and 0 gives me a 0. 0, 1, still, it's an and, so it's still going to give me 0. 0, 0. How about, and I'm just going to do this last little bit, just, it'll make my life easier. Okay, 0, 0, 0, 0, or, to make it a big long or, 0, 1, 0, 1. If either of these two bits are 1, then I will make it a 1. So it will be 0, 1, 0, 1. Notice what happens. With an OR, all the ones bubble up to the surface. They all stay. If there's a 1 in either of the numbers, it's going to stay around. With an and, if either one of those numbers is a 0, I'm going to get a 0. And so what you'll get is and bubbles up the zeros, and 1 and the or bubbles up the ones. Now let's have a look at some of these other numbers here. So 5 and 6. So let me just do this quickly. So 5 is 0, 1, 0, 1, and 6 is 0, 1, 1, 0. If I have a 0 and a 0, I have a 0. 1 and 1, I have a 1. 1 and 0, 0 and 1, I should say, gives me a 0. 1 and 0 gives me a 0. Oh, wait, that is the number 4. If I do 47 and 32, I will get the same thing. All the bits are going to go away. So or all of the, let me see here, all of the, if I don't have a 1 in both positions, I will not have that number. So notice 32 is one of my powers of 2. So you would expect no other number in that 47 is going to propagate through. 47 and 16. Is there the 16-bit on the 47? No, there isn't. Therefore, it's equal to 0. Let's do maybe a bit of an easier number. Let's do 13, and so we'll do 13. And since I did an and just then, I'll do an or. So let's do a 13 or let me see, 5. That may not work very well for me here, but let's see what we get. So what is 13 in binary? Well, it's almost going to be all one. So I have an 8, and then I have another 4, and then I have a 1 at the end. So 8 plus 4, 12, 13. All right. And here's my 5. It's going to be down here. It's going to be 0. If either of the bytes are on, I'll get a 1. 1, 0, 1. So that thing here is equal to 13. How about 13 and 5? If I did the same thing here, what would I get? I'm going to get, if any of those, either of those numbers is a 0, it's going to propagate out. 1, 0, 1. That's it's helpful to do a number of these examples on your own just to make sure you get a feel for it. So you can try 47 as 47 and 16, for example. Uh, so what are we doing? So what's the point of all this? It sounds like a weird trick. Why would we even have it so ingrained in the language? Well, it turns out that that trick allows you to do some interesting things. If you know your powers of 2, then you can actually represent each individual bit as a true and a false statement, and you can do some interesting things. So take, for example, if I have this value here and I AND it with a 0, a whole bunch of zeros, and a single 1. The only way that this thing will not be it'll be equal to 0 if I do not have matching a 1 and a 1 here. So in the case below, this one, this one are in the same position, the 1 propagates up, or it continues. And, as we've said a couple of times, we either have 0 as false, or not 0, which is true. Anything that is not 0 is considered true, and so even if a single bit is on, it is considered a quote-unquote true statement. So if I take this value number here and bitwise AND it with this number here, it will be considered true. If I take this number here and I AND it with this number, because I do not have a 1 in this position over here, then the entire thing is going to be zeros and it will be false. What this allows me to do is I can look at an individual bit. As a result, if an integer is 32 bits, it means I can have 32 true or false statements in one single number. So let's take another, or let's look at or in a second. But I also wanted to point out something else. How do I get this 2 to the power of I? I don't want to keep around or memorize all these powers. I don't want to have to know like, oh well, 2 to the power of 18 is, yeah, I don't want to remember that. There's another little trick that we have in C, and that is a bit shift. Bit shifts are kind of interesting. So first of all, let's take a 1, let's bit shift it over 2 positions. That means I'm going to add the number 0 at the end. So I originally had a 1, and then I add a 0 and a 0, a binary 0 and 0. So essentially, uh, that's going to be equal to 4. If I did 1 bit shift over, let's say, 4 positions, I will get a 1, 2, 3, 4 in binary, which is, if you remember correctly, should be equal to 16. Wait, 16 is equal to what? Oh, it's 2 to the power of 4. How about this? How about 2 to the power of 2, 2 to the power of 2 is, oh wait, 4. It allows me to do my powers of 2 by just putting a 1 and then shifting the bits over that many places. As a weird side effect, we can also do one other thing. We could just say, let's say, I don't want to do 5, let's do 6. If I shift over the other direction, I'm just going to shift over 1 bit. What is it going to do? It's going to take whatever number I had and shift everything over to the right. The arrows are going to the right. So here is my number 1, 1, 0. Let's do a 4-bit number, 4, 4, 6. All right. And then all I'm going to do is shift. So I get 0, 0, 1, 1. What is that number here? Oh, wait, that's 3. Wait, that's 6 divided by 2. Bit shifting to the right just divides it by 2. Now, notice if I do 5, so 0, 1, 0, 1, so this is 5, and I bit shift over 1 position, that's going to be equal to 0, 0, 1, 0, or the value 2. Because I divided 5 by 2, I get a remainder, but the remainder gets thrown away. Remember when we did integer arithmetic and we did integer division, if it was an odd number, if I divided by 2 and it's an odd number, I just throw away the extra remainder. I'm doing the same thing here. That's actually the fastest way to do integer division by 2. You can just shift the bits however many places you want. You want to divide it by 4, shift it over 2 positions. You want to divide it by 8, shift it over 3 positions. This is a little side effect or a little trick that you can use. I'm not going to be grilling people on that part, but knowing that I can shift over the bits one way or the other, playing around with it is a useful trick to have. It also means you don't have to memorize, 2 to the power of 17. So previously, if I want to see if a particular bit is on, this is what I can do. I can use and use it as part of my condition. If I wanted to see if I want to turn on a bit, I can use or, because doesn't matter what is in that bit over here originally. If I or it with a whole bunch of zeros and a 1, the one at the number or the bit at that position, in this case the third position here, will be 1 afterwards. It means all the ones just propagate to the top. If the 1 was already there, nothing happens. The number stays the same. It allows me, rather than using arithmetic and trying to add and then, oh, well, it's already in there, it's already on. Instead, it allows me to turn on the flag or flip a bit if I want to. If it wasn't on before, it's on now. If it was on before, it's left alone. You can think of this very much like a series of switches, where every single one of these bits in my number is a switch, and I'm just turning them on and off individually by using this kind of technique. So this allows me to turn on a bit. This lets me check to see if a bit is on, and we need to be able to turn them off as well. And so the one other step we can do is we can actually take a number and we can, if I use this tilde, this little symbol right here, it flips all the bits. So if it was this number here, 11011011, it becomes 00100100. No matter what, all it does is if it was on, it's off. If it was off, it's now on. It flips the bits. So I want you to pause for a second and think about how I could actually use that to turn off a bit. So what we had before, just to remind everybody, if I had some value val, uh, I could do this val, or, and I'm going to use all of our little tricks right now. So what is this? This is 2 to the power of 2, or the number 4. Uh, this is val, bitwise or the number 4. And what's that going to do? It means no matter what val is as a number, the position at the bit representing the number 4 will be on afterwards. It's turning on that bit. So whether it was on before or not, it doesn't matter. It's going to be on afterwards. We can also check to see if val is, so we can have things like if val and this would actually check to see if the bit, the position at the value 4, the third bit, I guess, third bit from the right, if the the bit that's representing the number 4 in your binary number, if that bit is on, then this will be a true statement. Otherwise, it will be considered false. And I want you to have a pause the video in a second when I'm done explaining things. I want you to think about how I might be able to use this bit flips, how to negate things, to actually save or remove a particular bit. So make sure that it is off. When I pick that up again, I'll show you the answer. And so you pause the video now, and then I'll go over the answer. All right. So for the two of you that actually turned this off, versus everyone else just went along and just waited, here's what we could do. Well, what I want actually is instead of, let's say if I have one, let's say I have this. What if I flipped all the bits over? So originally we're going to use a simple version of this, 0, 1, 0, 0. If I flip this, what do I get? I will get 1, 0, 1, 1. Okay. Now, what if I now use the and? So if I took some value val and tilde, what happens? Well, I'm everywhere except for that one position, they're all ones. So if it was in val before, it's in the new number afterwards. If it wasn't in val before, then it's still not in there. So if I had val be, let's say val is 5. Do I want 5? Val is, let's shoot 5. So this will be 0, 1, 0, 1. And I'm just going to simplify all of this. It'll be 1, 0, 1, 1. And now I go bit by bit comparing these two values. And this ends up being, it will be a 0, it'll be a 0, 0, and then the final bit is actually a 1. The only number that changed was this one right here, which happens to correspond with that 0 here. All the other numbers you're going to have, they're all going to just stay the same, because over on this side, I have all ones except for that one bit that I've changed. And this allows me to turn off a particular bit, which is kind of a nice thing to be able to do. All right, so we have bit shifting. We have single AND or bitwise AND. We have bitwise OR. Bitwise AND is used for if statements and for checking things. Bitwise OR allows me to turn on a flag. And notice I can also do some really quirky little things here, like what if I take a -1 and subtract 4 from it? Well, I could actually, if I have originally -1, I could actually just, if I subtract 4 from it, it will end up being, I will just turn off that 1 bit here. There's some other quirks that we can do, but let's let's have a quick look at subnet masks, and then we'll go and I'll show you another example in a second in code. So where does this actually end up getting used? Well, it ends up being used everywhere when it comes to networking. It turns out, if you look at a local IP address, for example, that here is an IP address right here, 172.17.9.170. And then we have this thing called a subnet mask. This is, by the way, literally coming from my computer like last term when I grabbed it. But here is an IP address for my particular computer where I'm routing information. Here is something called a subnet mask. And you'll notice, what is 255? Well, that is well, -1 as 2 bytes of, as 1 byte of information. Um, what we end up having is 1, 2, 3, 4, 1, 2, 3, 4. That's 255. We have the same thing here. 1, 2, 3, 4. 1, 2, 3, 4. I'm pretty sure 224 ends up being something along those lines of, and I didn't calculate it out, something like this. If I remove 16 from it, will it work? I'm going to remove the 16 position as well. About, approximately. And then a 0 afterwards. 1, 2, 3, 4. All right. 1, 2, 3, 4. What we end up having here is our subnet masks are always just a slew of ones and then a bunch of zeros afterwards. Now, it allows me to do something really cute. It allows me to just remove a chunk of the bits in the front or at the end, and so I can figure out what network I'm on or who the local computers around me are, without having to worry about the full IP address. So we could take this number here. I could then so 172.117.9.170. This is my binary numbers. And if I take this 172 and I do it bitwise and with all ones, that would be that first 255. What do I get? Well, I get the exact same number I had before. Here is the second number, the 17, and all ones again. I will get the exact same number I had before. Here is the third binary number, the 9, and with a bitwise and then I'm going to take, here is my 224. This is actually what 224 is. Hey, I was right. Good guess. So here's 224. If I do a bitwise and with this, the first three bits are zeros here. The first 3 bits are ones here. That means it's going to be all zeros afterwards. And then the last number is going to be all zeros as well. It allows me to just remove the front half or the back half of the binary number. So we can get the top bit number of bits with an and if I do an and with and flip all the bits and do an and again, I only get the bottom number of bits. I get the local network. And this is used throughout anytime you're dealing with a network. Uh, it's used all over computer science, but this is one of the classic examples. And if you want something a bit closer to home, however, here's literally a chunk of code that I stole from my own assignment for bit 2400. This is not me making something up. This is not my decision on how we go about doing things. This is how Windows actually checks to see if the control key is pressed or the shift key is pressed when you're dealing with a mouse. With a graphic user interface, this is actually what it does. It will tell you, you will get some flags variable from Windows when you get a mouse event. So when someone clicks a mouse, one of the parameters going into that event or that particular function, it's going to be called flags. And all you do is you check to see if I have a bitwise and with a control key, meaning is this the MK control bit in flags on, and is the MK shift bit in flags on. So maybe maybe flags is 1011 1101, and this is my control, and maybe let's make it a little bit interesting. And maybe that's just shift bit. It's just a number, right? So this is a value 2, and this is a value whatever that 16. Okay. If I did this, it would mean this has to be true and this thing has to be true in order for me to go into this condition. In this case, if I do this bit flags and that, what will I get? So let's do it one more time with my hypothetical scenario here. And I'm saying it's this bit here, so it's going to be 0, 0, 0, 1, 0, 0, 0, 0. I go bit by bit, check 0. Yeah. I go bit by bit, checking to see if I have a match. I get a 0, 0, 0, 1. The 1 and the 1 are match, and that because it's an AND, I need both of them to be on. I need both of them to be ones in order to get a 1. 0, 0, 0, 0. Well, this part right here is true. How about another? How about the other one? So 1, 0, 1, 1, 1, 1, 0, 1, and I said it's a second bit right here. Okay, so 2, 3, 4, 0, 0, 1, 0. What do I get? I get 0, 2, 3, and an and. 1, 2, 3, 4. Nothing. There is no column. There is no pair where both bits are 1. So this is false. I should say, I'm going to erase that. I want to erase that for a second. You'll see why in a second. Hopefully, if I can find my pen bit. There we go. I want to use double equals. All right. As a result, with this particular number, with this particular set of flags, the condition would not be true. But it's actually used all the time, and it's really kind of surprising how often it's used. Okay, last time we were talking about this, I said, let's have a look. Let's do this example. Let's do a 2D array of 6 by 3 2D array of floats, and then let's also make an array of 10 C strings. So let's 6 by 3 2D array of floats. All right, so let me make one of these. I'll go down to main in here just to demonstrate it. Okay, so a 6 by 3 array of floats. So if I have, do I want to do a dynamic array or not? I'm just going to do a static array here. That would be a static array of of floats. Well, what the heck, let's do a dynamic array. If I do a dynamic array, I'm going to need that for loop again, so that's not going to be so much fun. Let's do a one-dimensional version of this same array. So and let's figure out what I need to do. It's going to be a float pointer, and I'm going to call malloc, and it's a size of float multiplied by 6 multiplied by 3. All right, let's try that array of 10 characters. So I can do char star star text, let's call it, and I'm going to make It's the size of a char star. It's an array of pointers to character strings, or an array of character pointers. And then it's going to be size 10. All right. And then what I would need to do is something like this. AA text at position 0 is equal to hello. And let's do a couple more of these. Two. And I'm going to look at what the heck this error says. I'm assuming it's a constant character chart. So what I didn't point out is, let's just cast it this way. Strings such as this, where I just put in text, are constant character strings. We've seen that before, and therefore it's slightly different. They are the same under the hood, but you're not allowed to modify that text. You're not allowed to modify the word hello in this case, and that's why we have to do a cast here. So let's change a couple more of these. And modify them. So I'm going to go down one at a time. 2, 3, 4, 5, 6. Oh, I got lucky. Okay, and rather than hello, let's put a bye in here. Fun here, and then Susan, because I just like using the name Susan as an example. Okay, so here would be an array of characters, of character strings. And so I made my original array, which is just pointers to characters. And then for each one of those positions, I just hook it up to an actual character string, which is, so I have an array of arrays in this particular case. Versus up here, a I made a giant 6x3 giant. I made an array that just is one dimensional, but I'm going to pretend it's two dimensional. Or I also made a static array. If I was making a two-dimensional array, I would have something like this. So let's do that as well. And a float 2 is equal to float star star, and this would be malloc size of float star, and multiply by, well, I'm going to do 6, size 6 at first, and then I'm going to do the individual arrays afterwards. Okay. This will make an array, there we go. This is going to make just an array of pointers to floats. An array of pointers to floats, yes, that's right. And then afterwards I could do for int I is equal to 0, I is less than 6, I plus plus. And for each one of those elements, what I could do is make, I would then make an array inside. So a floats 2 at position I is equal to float star, I'll put space up there, malloc, and the size of float multiplied by 3. Each of them are 3 in size. And let's make sure that all looks good. That's still looking fine. All right, so for each of those positions, I'm going to make a brand new array and stick it in there. I'd also like to point out, hopefully if I didn't do it, I better do it. At the end of my function, when I have dynamic memory, I would like to point out again, if I have dynamic memory, I need to clear stuff up. If I have one of these two-dimensional arrays where I have a for loop where where I'm making the individual array inside, I still need to clear up. I need to call free on the inside arrays first, and then the parent array afterwards. So I need to, for each one of my rows, I need to call free to clear up the memory. And then after that, only after that, can I free up the main part. If I don't do it in that order, what's going to happen? I'm going to have all these pointers, and I'm going to lose track. I'm not going to have those pointers anymore. I freed up the memory, but I never gave back the memory to the system. I'm holding on to those pointers. I'm holding on to those arrays. I haven't given it back to the system. If I call free on the main part first. I would not have given back all of these individual arrays here back to the system before I give back the main one, the outside one. And notice when I'm done each time, I keep on, it's a good habit to get into, I set it to null. So, and for my static array, I don't need to do anything. It automatically gets given back to the system. If I'm not doing a dynamic array, I don't have to call free. Here is me calling free, by the way, on the one-dimensional array. And notice I don't have this, I don't need this for loop anymore. I just have to free all of the entire array all in one go. And then at the end of the day, I want to make sure it's set to null, just to make sure, just in case someone tries to access it, I want to know that I've given back that memory. If I don't set it to null, there's no way for me to know for sure that I've given back that memory. Okay, so what have we talked about so far? We've covered a fair bit of stuff. We talked about bitwise and bitwise or. I talked about bit shifting. We talked about masks briefly. And we also looked at how we went over examples of how to make arrays of memory. Let's see if I can do one more thing. And that is I'm going to do, just in case you don't believe me, here is int val is equal to, let's say 47. Great. I want to turn on an individual bit here. Val is 47, therefore I know the one's bit's on. I don't know if the two's bit's on, so we're going to find out. So I'm going to say val is equal to val or, and then let's do one bit shift over one. So I want to turn on the two's position. A one shifted over one is the value two. Just put a zero at the end. And I want to turn on that bit and save it to val. So whatever val is, it starts off at 47. I'm going to turn on the two's bit. Now, if it was already on, fine, nothing's going to happen. But if it wasn't on before, it is on now. Okay. And then I'm going to have if val and I'm going to do this one. And I'm going to do a printf statement just for fun. And let's put this /n in here. Okay. And then what am I going to do? I want to turn off that flag. So this is something I don't normally pick on for my students, but I'm going to do it anyways here. Tilde. So what is this actually going to do? This is, I have all the numbers are going to be ones except for the twos bit, and then I'm going to do an AND with it, which should turn off the twos bit in val. And then after that, I'm going to do the same test again afterwards, a test I don't expect it to pass, where I'm checking to see if that twos bit is on. Time two, something like that. Okay, so let's compile it. Let's see what we have here. And I'm going to put a breakpoint just to see everything in action. Okay, built. I'm going to compile it. I've already compiled it. Let's see what happens. So the value 47. Let's actually, can we look at it in hex? Is it hex decimal? No, it isn't. All right, the value 47, it's CCCCC. I'm going to move down one step. It is now 2F. The F would mean that I have all ones in the last 4 bits. So okay, so the ones the bit at position 2 is on. So what I expect is val bitwise or the number 2 is not going to change anything. And so we'll go one step in. Nothing has changed. If it's on, if val and one bit val and the number 2, if that bit is on, then I will go into this condition. It should always be true. Great. It prints out something. So now I'm going to turn off the bit. It is now 2D instead of 2F. because I just turned off the two's position. Notice it's D is two numbers less than F. I've removed the number two from this. And then after that, I'm going to check to see if I will go into this condition. So if the twos bit is on, the two bit should definitely not be on. It should there. So the twos bit here in the twos bit in val, there should be no overlap between the two, and I should not go into this condition. So I'll go one step further, and I jumped it. Okay, and if you don't believe me, one more thing I'm going to do, and that is I'm going to change val back. So val is equal to val or one. Let me turn the value back on just in case you didn't believe me. All right, so here we go. Nothing has changed. I go into that condition. I print something out. I turn off val. I turn off the bit associated with val. I turn off the twos bit in val. Okay, so I should not go into this printf statement. Fine. And then if I do one more step, if I do this or, what's going to happen? I should turn it back on. It should go back to 2f. Hey, there it goes. It went back to 2f. All right. So with that, I'm going to call it a night, and I will talk to you guys in a bit more when we're talking about pre-compiler instructions. Thanks, everyone.